Let's verify that everyone's streaming, and it is because I can hear it, which is a nightmare. All right. Cool. Let's ping people. Look how big this text is. No squinting needed. Okay. All right. Hey, there we go. Some people showing up. Cool. All right. Today, we're going to do the history lesson. Why is not my background working? That is a static screen that is appearing on Twitch. Just a second. Properties, display capture. All right. Cool. You can see that? All right. We're all set up. All right. We'll take it back to history lesson. What we're going to do, look at the Morris worm. So this is the inspiration for what will be BabyBot challenges. The Morris worm is pretty much was the first major instance on the web. It's like insane to think about, or not on the web, but on the internet. This was actually predates the internet. There were no websites back then. Websites came around 91, 92, 93 timeframe. So that helps you kind of situate things in your mind. So this was in November 2nd, 1988. RTM, Robert Tappan Morris, that's where the Morris worm comes from, was the one who was a graduate student at Cornell and launched it onto the internet. It was it then spread through the burgeoning internet and actually ended up taking down entire parts of the internet. They had to shut down computer systems for days at a time in order to patch them and fix them. What happened was there should have been, it kind of says this in here, but the worm was supposed to check if there was a copy of itself on the system, and if there was, it wouldn't actually propagate there. But what actually ended up happening is this worm ended up the check of the infection actually failed, and so the worm ended up copying itself 14% of the time every time it got to a new machine, scanned new machines, kept going. And so what happened is actually it was the worm itself that was fill up the machines, and they wouldn't be able to function because they were running so many copies of the worm that it caused problems. You can look up here replication rate, the effects. It basically took down a ton of the early internet, the ARPANET. But we're actually not going to get into the exact. Yeah, you can see 6,000 machines were infected by the Morris worm. But who knows how many there actually were, because however the numbers were created. And cool things that came out of it was CERT. So you've probably seen CERT is an organization to coordinate responses of emergency stuff. This was created specifically through there. So what we're going to do is go through and try to. We won't recreate the Morris worm, but we're going to try to identify the vulnerabilities that actually did exist at the time and what kind of things that they were looking at. We can actually see in here, it even tells us it exploited several vulnerabilities. And I think the cool thing is these weren't necessarily known, or sorry, the vulnerabilities themselves, or the idea of these vulnerabilities were known, but people didn't understand what big of a problem this was. And this was actually the big lesson of the Morris worm, is that people saw really viscerally what could happen if somebody programmed this worm that could spread this way. So we can see this will give us kind of our starting. You can kind of think of this as we're doing end day rediscovery. So we have this description. We have a hole in the debug mode of the Unix sendmail program, a buffer overflow, a hole in the finger network service. So finger D was a way to ask about different people on different networks. And this other cool thing, the transitive trust enabled by people setting up logins with no password requirements using remote shell The idea being that people actually it's not like they didn't have any notion of security, but what they said is, hey, this machine, if you're on this machine and you're a user on this machine, then you can automatically log into this other machine without a password. And this, you can see how this would be actually very easy and nice for people who are using these systems to be able to go across systems and use multiple systems. The problem here, of course, is that this establishes a trust relationship between these two systems. If I get access to host A, then I can easily get access to host B. And RTM knew this, and so use this as a way to propagate and spread the worm effectively without using any, whether it's a vulnerability, I think is kind of up in the air and interesting. Also, weak passwords. It actually did some kind of trivial password cracking. Maybe if we have time, we'll get into the worm itself. I don't think we'll actually have that time, but don't. So actually, this was like one of the earliest days, just to kind of go forward. Morris, RTM was tried and convicted of violating the Computer Fraud and Abuse Act. The other crazy thing was that, let's say up here, that RTM's dad, yes, it was the son of cryptographer Robert Morris, who worked at the NSA. So maybe there was ideas of security floating around in that family or in those heads. Who knows? But so even though he was sentenced to 3 years probation, 400 hours of community service, and a fine, but it turned out okay. So RTM is a professor at MIT, if I remember correctly. Why is it not? Yeah, professor. He also helped start a company called VioWeb, which you probably don't remember, which was bought by Yahoo back in the first .com boom, and helped create the Y Combinator company and startup incubator, if you've heard of that. So yeah, doing good, has convictions on here. Interesting. Cool. Okay, so let's dig in. So first, I am definitely cheating. So I'm not, going to show you this. Well, I will show you this, but anyways, I'll post it. I'm using this great blog post of the Ghosts of Exploits Past, a deep dive into the Morris worm. This was a blog post for somebody written where they have got running in a almost easy to use. It didn't work right off the bat. I'll maybe push the changes that I made. A Docker file or a Docker container that we can look at it here. Sorry, I will increase the font size. If you can't see my screen, please let me know. Looking here, this is the Docker file, and what it's doing is running a BSD 4.3, which was released in, let's see, where do I have it here? BSD 4.3, which had TCP/IP networking, that was released in June of 1986. This is older than I am. Yes. Which is kind of cool. And so people actually have a lot of cool, there's a lot of cool effort into preserving this kind of computing history. So what this uses under the hood is the SimH. So it's a simulator for historic computer systems and also kinds of things. It's basically a simulator that will run many types of things. It has, like you can see here, all the different types of things. PDP-1, PDP-4, 7, 8, 10, 11, IBM machines, HP machines, all kinds of crazy stuff. So this is running we're on the VAX 11, if I do recall. So this is, and if we look back at the worm, we can see the worm targeted VAX machines, Sun machines, and some other types of machines. The cool thing about the Morris worm, and why it's like a cross-platform worm, is it actually would copy its source code to the target machine, compile it, and then run it and execute it there, which is how it achieved its functionality. So it's an 88. So we have here in this handy dandy Docker container something that has the 4.3. Yeah, so this is BSD 4.3. It has boot files, all kinds of stuff, a mini root directory, and all the information to run this. So it's running the VAX 11 simulator. That's exactly what's happening. Um, this is all the boot up commands. I already pre-ran this because it takes like a long time for this thing to run. You can see we're running 4.3 BSD from June 6th, 1986 was the thing. I guess if this maybe was the person or maybe the machine that we got it from and the specific location. Memories, I don't know. This is just it booting up. When we get to here, we have a login. We're bad people. We're going to log in as root. It's going to tell us don't log in as root, use SU. So you can actually see, like, even in 86, they were thinking about, the either security or honestly probably just the, like, not crashing your system by running as root all the time. Would you like to play a game? So we can look. Hopefully this is super cool. What I really like about this is seeing that getting your way around the command line, even in the modern day, you can understand and appreciate how a system in 86 was built because it uses the same interface. That BSD style, kind of Unix style thing became what we all kind of use today in the POSIX standard and all that fun stuff. Okay. So we can look at our present working directory. We're actually dropped into slash, so we're in slash. Cool thing that I like, slash bin. So these are all the programs we have available. It's actually a decent amount. I don't know what all these does. Awk, cat, you're definitely familiar with. CC is a compiler. H. Okay, don't know how to make it tell me help, but oh, it does have a strings command. That's wild. Absolutely wild. Okay. Oh, it doesn't, up and down don't work. Maybe, I don't know if that's a shell thing or my Docker container or whatever. But, so we can see CC 4.3 from 1985. I wonder why it didn't show me the help output. But anyways, so there's just a lot of cool stuff in here. And all this, change group, chmod, change shell, compare, copy, date, dd, df, diff, du, I don't remember what this is. Echo ed is the command line editor, if you're wondering how people edited files there. False grep, like, think about it as you're using these tools, right? It comes from this very long lineage of tools. Mail, sending mail is very important. Make directory. Okay, anyways, all cool stuff. Okay, and we can start with the buffer overflow in the finger program. So let's look at, okay, yeah. So the cool thing about this distribution is if you think, hey, this was a system that you had access, maybe you had access to an internet or the internet, but the source code, actually, I don't know if it was always on these systems, but the source code is available on this system here. It would make sense if it was distributed. So I can see a bunch of there's all kinds of stuff. I bet we could probably look at some of these and find lots of bugs. Actually, maybe we should do that. No, let's start with something that we can definitely do and finish within 45 minutes. Okay, so finger D. So this is let's look at what the finger, what was the point of this protocol? So finger was created in, there's always an RFC for it. So RFC 742. That's what I love about the internet and these things. They're all documented. You can learn about this. Describes the name finger protocol. There's a simple protocol which provides an interface to the name and finger programs at several network sites. These programs return a friendly, human-oriented status report on either the system or a particular person. Currently, only SAIL, SRI, and ITS sites support this protocol, but there are other systems with similar programs that could easily be made servers. Cool. Yeah, so it's a pretty simple protocol. Let's go in here. Name. I wonder if there's name in here. Name D. So there's probably a name daemon here. Provide status reports on a particular computer system or a particular person. So name was for the system or the person, and finger was the person. So yeah, so basically like you can kind of think of this as like super early social networking, right? They didn't even have this concept of computer social networks, but you wanted information about other users on the network and other users on other systems. Yeah, what you had to do is use who. So that's why on a lot of systems you type who, right? It shows you the users that are logged into this. You can do this on any system you have access to, and it will show you the currently logged in users. And that's how you do this. But this is how you could do it remotely. So why they called it finger was because you saw users of the system run their fingers down the output of the who command to better see who is there. Of course, this is Wikipedia, so who knows what these sources are, but hey, take the grain of salt. So it runs on port 79, which is good. Important to remember, the client will open a connection to port 79. Remote user information program start on the remote end to process the request. The finger user information protocol is based on RFC 1288, so there's a protocol for that. Although this was written in 91, so we have to understand that that's maybe describing this, but not necessarily going to be perfect. All right. Cool. So let's look at that code. Show me the code. Okay. Okay, that doesn't work. etc. Cool. All right, so we don't have it. Oh, wow. This is very small. Love it. Let's see. We want to audit this. Let's audit this in a nice operating with my beautiful Emacs with all the syntax highlighting. Of course, this is definitely not going to come back and bite us. Fingerd.c. All right. Cool. Look at that. Giant. Okay, so copyright. From 1983. Interesting if this was. This is 85. So looking at stuff with this is older even than the operating system where it came out, right? So we can look at this. This is kind of crazy. I remembered when looking at this, I wonder, is argc, are they not using this? Yeah. So this is definitely not like a modern style of C, although I don't remember where the trade-off was. I wonder if I have my C book. I have the K&R C book. No, that's the standard library. Maybe I have it at home. Hopefully you have a copy of the K&R C book. So you can see that like they declare the types of the variables even after the function. Let's see what C syntax. Yeah, here we go. So this is one of the cool things I like looking at super old programs. You can see that that's the old style syntax for parameter lists, which is still supported. In KNRC, you would also leave out the type declarations that would default to int. So that's why, like this example here, we didn't have a declaration for argc, but we quote know it would be an int. Now this is insane. I mean, this is clearly the benefit is having the types right in here is much better from a usability perspective. So this is KNR style. Okay, so that's the thing. Other things, if you've never seen it, this is a register is a C keyword. This, I believe, tells it to keep that into a register. But yeah, we can just read through this. So declare some character pointer SP, align buffer, so buffer of 512, sock adder in S in. If you've been following along with pwn.college stuff since 365. You're very familiar with the sock adder in. You can see it traces all the way back to the early days of the internet. I, an array of ints of p, PID status, a file pointer, and AV. Okay. So first get size of, okay, yeah. So I is the size of this structure, this struct sock adder in, and then check if get peer name 0, nah, is that probably getting our peer name? I wonder if we can even look up the documentation. BSD 4.3 get peer name. Oh, sick. I can't believe this actually works. Or that this stuff here is. Okay. So the get peer name system call, so it's a system call into the kernel, returns the name of the peer connected to the socket S. The name like argument should be initialized to the actual amount of space. On return, it contains the actual size of the name. The name is truncated if the buffer provided is too small. The question is, why was it passing in 0 here? I wonder if that's our name. Oh, wait, because that's, I wonder if we can get the 4.3 docs. Okay, returns the name of the peer. Oh, 4.2. Get peer name socket 0. BSD. It looks for the peer that is host file. Oh, file descriptor 0. Oh, standard in. Okay. So it's okay. Great. So this makes a lot of sense. Fingerd was actually run using inetd. So inetd is a program that basically you could specify other programs. This way you wouldn't have to write networking code. You could write standard input, standard output code, and it would automatically go there. Actually, a lot of CTF challenges, not in pwn.college, but on actual CTFs, where they run, you're reversing a binary that uses standard input and standard output, but it's running on a remote system that you hit over the network. That's because of inetd. Okay, this makes sense. So it actually is, the socket is 0, or the file descriptor, which is 0, is standard input. And so the idea is you'd have to run this for standard input being redirected to a socket so that it can get the peer name. Because you can see the get peer name, if it fails, so if it's less than 0, then error out. Okay, line 0 is the null byte, so nulling out just the first 0 of this buffer, and then gets line, and then sets SP equal to line, sets AV0 as finger, while 1, if it's a while we point to a space, increment the pointer, so keep going until we don't point to a space. That's what this does. If we're at the end, so if we dereference SP and it's 0, then break out of this infinite while loop. If it's a slash and the next one is a capital W or a lowercase w, then advance it to and add the argument to AV-L. So it's going to be finger -L. If we're pointing to something, which is redundant because we had this check here, but that's fine. We're being extra careful. If we are pointing to something and it's not a space, which also, again, these two just happened, so it should be impossible for that to actually be true. Oh, but no, we did this SP plus equal to 2. Interesting. Okay, so this is a check. See? Complexity, even in super old stuff. So dereference it, then AV, this argument is here equal to SP, while star SP, that is not space, SP++, and increment it, and then set a null byte there. So this vector AV is a vector of strings. So it's setting up, it looks like arguments to finger. So it's doing finger, blah, 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 blah. Create a pipe, fork, if we're 0. Okay, this makes sense. Close it. dupe it, close it, execv. Yeah, okay. So we're calling slash user UCB finger. So this is the local thing that we're calling user UCB finger. We're passing in this array of arguments. So the first argument will be finger. The second argument, there could be a -L depending on if we have /W or /w as part of the input line. Otherwise, these will be there. These will be arguments that are passed to finger. And then we call that, and then that, whatever that is, that looks like that will be returned. Yeah, get C from the file pointer. We're reading from that pipe that we executed. Okay, so interesting. So super, this is actually I think smaller than a lot of the pwn.college challenges, or maybe on the same-ish level. But you can see that it's actually fairly simple. So everyone out there in Twitch land, where's the bug? Your RTM, where's the bug? Maybe I'll just wait till somebody writes something into the chat. Yeah. All right, cool. People just joined. So we're looking at source code of the FingerD service that runs on the VAX. Well, it's C code, but it's made for BSD 4.3, which was released in 1986. So we're looking at super old code. All right, so what's the bug? We can look at, boom, one line, gets. So let's look at the documentation. BSD 4.3 gets. Where was the BSD documentation? System calls, let's say all sections. Just show me the gets. There we go. Gets. So the gets function is equal to fgets with an infinite size and a stream of standard in, except that the new line character, if any, is not stored in the string. It is the caller's responsibility to ensure that the input line, if any, is sufficiently short to fit the string. So this is clearly what it's saying. It's the caller's responsibility. How in the world, if you are calling gets, how can you ensure that infinity will fit inside here, right? Fundamentally, and especially this is what they didn't realize, is when you're then taking input from an untrusted source, this is the root of the bug and the major problem. And this leads to a buffer overflow. So we can, looking at here, oops, I calculated that, gets line will read in from standard input, or in this case, not standard input because it's the, it is a remote process, but it's going to read into line. It'll read, this is only 512 bytes. It's going to read 512 bytes and then continue reading. Okay. So now that we understand that, we understand the bug, so we should just be able to trivially bypass this. I bet there's another bug if we looked at finger, so user UCB finger. Let's look and see if we have that on our system. Yep. Root, Charlie root. That's interesting. And it would just probably output this. So let's look at what that user. Yeah, so if you give it arguments, login name root, it'd tell you the directory that they're currently in, the shell, it would output a plan, cat etc. Interesting. We actually have a lot of people on here. I wonder if this is from a real system. So we could do things like finger. Stephen Falcon, is this a real person? User War Games. No, maybe this is from War Games. Anyway, we can see there's a bunch of, Dennis Ritchie, Ken Thompson. DMR, Ken. I wonder what these passwords are. That's interesting. Okay, but anyways, so we have all this stuff. We can definitely, from a remote perspective, we can talk to this. And let's test that. So it's 3:30. I want to make sure we can pop this. So I wonder, let's see, where was the source code? The source code was, yeah, user source. And that's in there. UCB. Let's see. LSI, user source, UCB. Boom. There's the source code of finger. Okay, I've got to know. This is okay, see, that's much larger. But the input that we have is very little. Except we control argv, the arguments. So let's see. So there was a trivial one there. Let's just look at this quickly so we can see. I don't know. Maybe it'll be nothing, but I think it'd be cool to see if we can pop this different service, but similarly. Oh, here we are. Let's just look through this here. So argv. So imagine we can control any values to argv. We technically do have some limit because well, whatever. Okay. So parse command line args for optional arguments. We can actually we can set any of these. Hack. Interesting. I like hacks. Default. Oh, if we give it anything / it'll give us that. Okay, cool. Do all. If argv is 0, it gives everyone. Otherwise, I do names. So that's where we want to go. Do names takes in argv, so we control argv. Let's see. Net finger. Name. If name is null, return 0. Host. R index name. Get host by name. Host. We're getting kind of deep. Oh, name buff. I like that. Okay, inet adder. String copy host into name buff. Cool. So it's very clear if we had something there, we could have done that because any string copy is basically vulnerable. All right. We're getting too deep. I want to not do this. Yeah, because I really wish. Anyways, okay, let's go back. We'll exploit that gets. All right. Now the problem is this get peer name. We will have a problem. Yeah, so we have etc finger d here, but if we try to run it, right? So see, it's doing a socket operation on non-socket because this program is meant to be run from inetd. So we're going to cheat a little bit. We could probably set this up with inetd. I really don't want to do that right now. We're just gonna. We have the source. Let's just get rid of that source. Where was? There we go. Okay. etc. Oh no. Hey. I have no idea why I can't see anything. Let me look. Time to cheat. That's why I got it. Okay. Where the heck is it? Okay. sharing it on here? Is that where it is? Oh, okay. Okay, here we go. Okay. VI. Whew, it's gonna be tough. Okay. Okay, let's see. CD temp. Let's see. Copy that to here. Okay. Let's check. Okay. Okay. I cannot edit this way. Oh, duh. Easy way. We do that in here. You go boop, 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 boop. And we should have file redirection. Control D. And we can cat it out just to double check. All right, we can compile it. CC. We'll add G for debugging. Oh, look at that. It worked. Okay, we compiled it. Let's run it. Beautiful. Okay. I can say A. This actually is shelling out. Okay, now what if I do this? And then let's say my input is a lot of A's. Not enough A's. Interesting. Okay. All right. Why? No, there's no Perl here. Okay. Great. So somebody in the chat saying, I remember CTF wants use finger D in the pwn category. Yeah, that makes sense. It's these are classic, like, historical vulnerabilities, so it makes sense. Okay. So, I know what we can do. It's kind of janky, but we need a line without any spaces. I wonder if we went something like this. Type it to finger D. Okay, that did not. Well, how can we tell if we crashed it? Okay, that doesn't work. Okay, so what we need is a giant input. So gets should have absolutely no. So we had 512 here. So what we're going to do, and we're going to use a trick that I haven't actually used before, but so we'll be on the same system. We're going to use Python print /x or just a times 2048. Okay, that will give us a bunch of A's, definitely enough to crash it. And what I'm going to use is, I've never used this before, UU encode. input and so okay, that doesn't work. Okay, you encode and install. Go to 2204. Jar utils, obviously. Let's actually look at this. I want to see what this looks like. Oh, interesting. Begin 64 input.bin. So yeah, this is great. Okay, so it's just a way of encoding it, and it will actually save it as that file. Okay, and we're doing netcat because we're going to use this crazy way of config. Well, actually, I can do this kind of jankily, but I don't need netcat. I can do something like this. Let's say, oh no, I can't pipe it through PG copy. It's on another thing. I can do this, and then I can say here, kappa UUD code. Boom, have input.bin, a bunch of A's, and I can cat input.bin, pipe that to finger D, bus error, core done. Woo, 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 woo. Okay. Sick. So now we know we can generate input to trigger this bug. So GDB actually comes from a much earlier debugger, DBX. So yeah, here we can see from 86, help, we can actually, you can see it's much more verbose in some sense than GDB. We can definitely see the lineage. Okay, and it actually uses line numbers. So let's, okay, what we want to stop at is the return statement, which is on line 85. We can see here in my editor. This is where we want to stop. So let's say it is stop at 85, run input.bin. Oh, interesting. Bus error and gets. I wonder if I can say, where's the trace? Okay, hit size of gets interesting. Okay, so I have absolutely no idea what Invax move C3 is. I think I'm probably erasing too much, or it's. Oh, I wonder if I have programs like head. Let's see, input.bin. Okay. The format is different. There's no help. I guess I can always read the source. This is what you're supposed to do back in the day. You were supposed to just read the source code of whatever, figuring out how things worked, which isn't a terrible idea. Okay, we're going to do something different. I'm going to cheat using this thing. So we have our UU encode. instead of a bunch of freaking A's, what we're going to do is actually use the debug. So hex 3 is the VAX BPT or breakpoint instruction. So we're going to do 03. Now, probably what I'd do with this is I'd figure out how to make this work, but I want to get us to a point that's cool in 15 minutes. So let's do 512 of these, followed by 16 null bytes. Wait, is it that? Why can't I remember how to do this in Python? I think it's like that. We'll double check it. Times 16, and followed by, now let's say this is X dump. Great, bunch of 3s, 0s, and a new line. Okay. All right, another UU encoding. So now UU decode. Ah, shoot. Okay. Okay, good. Cat. Cool. Segmentation fault, core dumped. That is what we want. Ooh, we get the core dump. DBX, finger D. Oh. Interesting. Oh, it's reading that core file. I don't want you to do that. It did automatically. Okay. Oh, sick. Okay, wait. We don't want to do that yet. We want to actually debug. Stop at 85. Okay, cool. Now we can check X, not 5. Yeah, that's not the right syntax. So we need to look at, this is looking at the next 10 instructions of the program counter. We have CLRL R0 ret, and then a bunch of other stuff. So CLRL R0, oh, clear R0 because we're returning, probably clearing it because we're returning 0. So R0 must be the register that we're returning into. So if we do next or step I, so now we're at this ret. So let's look at 20 long words from our register, so from the stack pointer. So this is what where we are on the stack. We have going up 00002080, some pointer here in memory, a bunch of 3s, the 0s, and then our 41, 41, 41. We can see that there. And we are, so let's look at our frame pointer. Capital X. Cool. So that was our 4 zeros and the 41, 41, 41. So now if we do a step instruction. Oh, is this x86? Heck no, it's not x86. This is VAX. So sorry, yeah, thanks for the reminder. This is VAX assembly. Because this is, the machine that this is a VAX 11. So this is for sure not x86. We could probably look at like CLCR. Yeah, here's the instruction set. Wait, where was that? CLRL, CLRL. did I just CLRL? Yep. So clears the long word at there if blup is defined in absolute mode. So it clears, I think, what's ever in the register. So R4, yeah. Clear long. So that clears a long. Let's look up ret. Yeah, we're diving deep. We're going deep. We're going to exploit this, hopefully. So ret is at 969. Oh, we can see 8, so 9. Here's all the instructions, compare, blah, 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 opcode stuff, move instructions, skip character, CRC, that's interesting, embedding that in there. Add, shift, where are you, ret? RSB is returned from subroutine. Was it actually RSB and I just called it ret? No, it's called ret. Procedure call instructions. The following 3 instructions are a standard procedure call. Call G, call S, ret. The return instruction returns from the procedure. So the entry mask specifies the register use and overflow enables of the sub-procedure. Whoa, that's insane. Okay. Whoa, call G instruction calls a procedure with the argument listed in an arbitrary location. That's pretty crazy. The call S instruction calls a procedure with the argument list on the stack, which is what we're more related to with x86. Calls a procedure with the argument. Upon return, this list is automatically removed from the stack. Both call instructions specify the address and entry point. Consists of a word called the entry mask followed by the procedure's instructions. Whoa, that's crazy. Okay. What does the ret do? In addition, the program counter, stack pointer, frame pointer, and argument pointer are preserved by the call instructions and stored by the ret instructions. So I think, if you remember correctly, we have this 1, 2, 3, 4, and then this. I think this is our, so this is probably the last one is the program counter because that's the one that's actually done. It's probably program counter, stack pointer, frame pointer, argument pointer, and maybe, I don't know what this another thing is. Huh. To preserve the state, the call instructions from a instruction on the stack from the call frame or a stack frame. The call frame contains the save registers, the save PSW, the register save mask, and several control bits. Control bits. Oh, this is so cool. Frame also includes a long word that the call instructions clear. Oh, cool. The stack frame has the following format: a condition handler. Let's see, half of a thing, this mask, this PSW, saved AP, FP, PC, R0. Wow. So this is where the FP is. Okay, so 1, 2, 3, 4, 5. That's what we're looking at. So this is the frame pointer. This is exactly what we're looking at. This is the frame pointer. We have frame pointer here. That's the condition handler. This is this next junk. This is saved AP, saved FP, and then PC. Wow. And then actually is all the other registers and stuff. Oh, you could prop like so easily with this. This is so cool. You get stack control. You literally control everything. Cool. Okay. And if we do a step instruction, we get stopped because we tried to write at 41, 41, 41, which I'm not sure. I guess there's memory there. Is that what's happening? All right. So one of the cool things is we actually know exactly where our buffer starts. So we can basically, and there's no there's shellcode on this stuff. There's definitely an executable stack, and the stack location is going to be perfectly fixed. So we can actually use, this is what, 1, 2, 3, 4, 5, 6, 7, 8. So we can use this. So this is I'm going to use a calculator because good old handy dandy calculator. Nope. Good old handy dandy calculator. So that's here, +4, +4, so +8. So that's the start of the buffer. That's what I want to hit. We actually do need to make sure that there's no spaces in here. I think we're fine with 40 E9. Still even back in the day, you got to worry about that junk. So let's do. Yeah, so now let's change this rather than these A's. We'll go /x40 /xe9 /xfe /x 40 E9 FF 7F E9 FE FE EF 40 E9 FF 7F. This is why Pwn Tools is so great, because typing this in just background 7F FF E9 40. Let's do that. You decode this guy. Asha! When it got to the end, it just automatically did this. Don't worry, everything's still persistent, even though this is frustrating. dbx. Oops. That's an interesting. Run. Okay, stop at 85. Let's see, we're gonna ret. Let's look at that frame buffer. Boom, boom, boom. Why did that get translated into 40 E9? Is E9 a space character? It makes sense. Huh. I guess we can decode those instructions at least. Let's say, what if we did? Okay, well, that is what's there. This escape CF, and that's what was borked. All right, I'm going to cheat. Just use whatever the heck address they freaking used in their demo. So 7F FF EA 38. Okay, boom. Okay. dbx finger D. Stop at 85. Run input.bin. Step instruction. Look at FP. Okay. Where are you, FP? Okay, something is not right. Let's hex dump this. Oh, is this a UTF-8 thing? Oh, it freaking is. 7FBFAA. Okay, that's, yeah. Oh, man, this used to be so much easier. Python print bytes. Okay. Import sys dot standard out dot buffer dot write. There we go. 7FFFEA38. See, this is the problem. When you take it all the way through, you think there's a problem there, but I never checked this first part here. All right, you know what? We're using our freaking addresses because we found them. 7FFFE9 40. Boom. Okay. UU encode. Okay. And the finger D. Stop at 85. Step instruction. All right, the FPs. Show me those beautiful FPs. I want to see it working. Yeah, sick. Okay, we've overwritten that. So now if we step again, what do we think should happen? We think that control flow should be redirected here. And what did we put there? If we do blah, blah, 10i, breakpoints. Boom, stopped. Boom, stopped again. All right. Okay, BSD VAX shellcode. Now, let's do some stuff. There's actually all kinds of crazy stuff. There's even allegedly there's in Metasploit has BSD shellcode. Push L0, push L blah, 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 host, if net plus port. This does a reverse shell. I want like oh, that's the only one they have. Does anybody just have normal shellcode? All right. Maybe, should I leave this as an exercise to you? Oh, that's funny. Wait, this is an older one. Okay, this is stupid. Why is this in here? So you can exploit. That's lame. Just do it yourself. Oh, 01 is not interesting. The return address. Shellcode. Where's your shellcode, my friend? Could write it ourselves. I don't want to, but you could write it yourself. You could probably figure it out by the output here. This, let's see. Disassembly. It's like 100 bytes. I don't know what chipmunk is. Pushing things. I think it was what we saw in there. Those are like the IPs and the ports to connect to. Let's just see. Maybe we can use this if they use 192.168.1.3. I don't know. There's nothing there. We can for sure probably just modify those bytes. Since we saw in Metasploit, yeah, where this is. Yeah, this is the host port. And what did he change? What did they change here? Oh, I see. All right, I'm probably gonna go a little late because I want to see this freaking pop. I pretend to be that. Oops. Oh, I copied too much. Beware what you copy. Okay, IPv6 is definitely not going to work. Let me look. Oh, but maybe my Docker? Do I have 127 Okay, let's verify that we can do this. Netcat, listen, keep open 4444. Telnet 10.218.105.27. Okay, let's see if we can ping. Okay. Rats. I don't know why that was. Okay. NVL. Am I not doing like this? Oh. All right. Thank you. Let's see. The question is, does Telnet? Remember the Telnet? Oh yeah, it is like that. Okay. It's got to be like hard coded or something. Like we just don't quite understand how the packets are flowing through here since this is in a weird network running in a simulator. Yeah, I don't think there's Netcat on this machine though. Yeah. Okay. Networking. Okay, well, I think we did our best. I think you're at a place where you could probably even take it from here and actually write a full exploit for this. You could even probably do some cool ROP stuff, which we didn't talk about, but yeah, that's pretty fun. Will you need it for the module? Oh, no, for sure not. You're not hitting any VAX machines, at least as far as I know. This was more of just like a fun trip down memory lane of really digging into the putting yourself in the shoes of RTM and exploiting things. So, yeah, I don't know. I thought that was fun. So hopefully you liked it. If not, I don't know. Thanks for hanging out. See ya.